Good evening, everyone. Welcome to CE3372, Fall 2020. This is Lesson 17, where we're going to go through the rational method for sizing storm drain conduits. And we'll take a second here to connect to the Blackboard server. I'll call your attention to exercises that have been posted. So there's one exercise set 6, which is application of Manning's equation in some simplistic geometries. So this is a fairly straightforward exercise. It has 4 problems, problems 1, 2, 3, and 4. In problem 1, we're told that water's flowing through a particularly dimensioned rectangular channel, and you're to calculate the flow depth and answer a series of questions relative to those calculations. Question 2 is a trapezoidal channel, and some smart aleck gave it to you at 293 degrees Kelvin, the most common temperature measuring unit in the history of the world, not. Then the third one is a circular sewer, which will have some relevance after tonight. And the last one is a road swale, which is also another variant of the trapezoidal channel. In addition to that, there's exercise set 7, which is direct application of the rational equation method. So this will be a review of hydrology. So we're given this study area here. We're interested in the behavior on this rectangular blue shaded area on the screen in front of you. And each of the dots represents an elevation measurement. And we're told that the rectangular area is 250 acres. We have a high point up here at 150 feet. Low point's 139 feet. We don't actually have any observations south of that. So that should make an interesting contour map. So your procedure is to create a contour map, draw representative overland flow paths, draw what you think is the longest flow path from the highest elevation to the outlet that's entirely contained within the 250 acre study area. Draw a shortest flow path. That should be pretty easy. I can do that without any thinking. It's the one that essentially goes straight down corner to corner. Determine the length in feet of both those flow paths. Determine the average dimensionless slope of each flow path. Estimate the time of concentration. I recommend the NRCS upland method, namely because it's simple. That's the one that involves the chart that have pictures of different overland flow characteristics, and you enter it with slope and you recover velocity, and then you divide the distance by that velocity to recover time. Then using that time of concentration and NOAA Atlas 14 Volume 10, estimate the appropriate rainfall intensity for a 10-year annual recurrence interval, 3-hour duration storm, and we're told what county this is. Yeah, Harris County. And then using an appropriate runoff coefficient table, this is pretty much just up to you. Just find a coefficient table that you can cite and pick a runoff coefficient for that area. Estimate the peak discharge using the 10-year annual recurrence interval. So you'll be using what you determine in step H directly. And finally, attempt to construct a design hyetograph at 15-minute intervals. It says use the SCS tabulation or text hyeto. The SCS tabulation as presented will not correctly produce a design hyetograph. So use the Texas hyetograph method for that. And that is exercise set 7. So that pretty much takes care of the preliminaries that we'll need for the next few exercises, which will be the drainage part of the Somewhere USA subdivision, and we'll combine the two for the final project report. And I'm aware I haven't talked much about that yet. I won't get to it today. And today's lesson is down here, lesson 17, storm sewer conduit sizing. And we'll take the link to the content server. The lesson description is conduit size selection. So these are, I consider these initial estimates using the rational method storm sewer design. We'll go through that in some detail shortly. The video links, none of them are active except for this storm drain hydraulics, which is a 2018 version of the lesson we had last time. And in the data links, the spreadsheet scripts is important because it contains the examples that we'll look at today. So in the notes, there's a series of potential readings. There's storm drain design, which is directly from the Land Development Handbook. We glimpsed at that last meeting. Urban stormwater management, which is the latter part of Werb's and James. And the only stipulation is it looks like this was photocopied backwards. So the arrangement of the individual pages is opposite of how a normal human being would read it. So keeping that in mind, that as you look at it, you'll have to read it by following the page numbers. So that has a pretty good description of what we're talking about. In Chen on page 479, same kind of information is presented. In fact, there's a nice example that's a very simplified version of what we'll go through today, and illustrates how to make the requisite calculations to size pipes. In this particular example, he has two sub areas. Catchment A here drains to inlet number 1. Catchment B drains to inlet number 2, but inlet number 2 also receives runoff from catchment A through this pipe number 1, and so the rational method can be used to size this pipe. Then these can be gathered together and size this pipe and moving on downstream. So this will make a little bit more sense if you've never seen it in a moment. There's a slightly more detailed example for sizing pipes presented in this reading right here, called Drainage Design by Rational Method. So here there's 3 areas: Area 1, Area 2, and Area 3, and the associated inlets for Area 1, Area 2, Area 3, and there's a pipe here, pipe number 1, another pipe, pipe number 2, and there's 3 junctions called manhole 1, manhole 2, manhole 3, and this example goes through sizing pipe number 1 and pipe number 2 using the rational method and a particular intensity model. So you could go through this on your own. I think it's actually pretty sequential and straightforward, where it shows the computation of the inlet times, the addition of manholes, the location of pipes, and then finally the connection of the inlets to the manholes, and the overall design procedure of these CA values and so forth in order to determine the pipe diameters. So I'll let you read that at your own time, and we'll move on to the lesson notes for today. It's there are no PDF files because we've hit new software where everything is huge file sizes. Do the okie dokie on that. I'm sure that's a mistake. Good luck finding money in this PowerPoint file. So let's see how to turn this into a, there we go. So lesson 17, storm sewer conduit design by the rational equation method, fall 2020. The purposes of conduits are to convey storm flow from one location to another. And that's done in pipes, culverts, and open channels. So all three of those are representative examples of conduits. Today we'll focus mostly on pipes. And conduit design narrows down to the selection of the size, the diameter, the material, and the slope that the conduit is going to be placed on. The usual materials for stormwater are going to be reinforced concrete and maybe some of the modern plastics, high-density polyethylene, spun polyvinyl chloride, and so forth. Clay pipes used to be common, but their use is fading away. Not that there's anything wrong with a clay pipe. It's actually a really good material for stormwater and for sanitary, but it requires a level of placement skill that's not economical to find anymore. So it's becoming less and less used in new installations. A clay pipe is likely to be around for quite a while to replace existing clay pipes as they fail. Ductile iron is not often used in sewers except in portions where we're going to be pumping water, and they'll be relatively short because storm sewers generally are designed and operated as if they're going to be open channels. A sanitary sewer, a similar design mentality. Sanitary sewers probably have more material selections, and they tend to favor the modern plastics rather than reinforced concrete pipe. Because one of the added bonus features of wastewater is that they, under low oxygen conditions as they're encountered in a sewer, they can generate sulfuric acids and slowly damage the cementitious materials that hold a concrete pipe together, and then you get the ultimate failure of the system at some point in the future, and it doesn't fail at any place that's nice and convenient. The size or the diameter of the pipes is dictated largely by the flow that it has to carry, and to some extent by the burial depth relative to the total drop that's available. And by drop, try to draw a sketch of what I mean by drop. So we click on the pen. Let's suppose we have a very poorly drawn manhole here and one down here, and then this is going out to our receiving stream. So the drop is this distance. And if the earth is up here, pretty rugged earth right there, there's usually a prescribed cover that's required so that we can drive over that pipe, a big mag wheel attached to our car, and not crush the pipe. So I've done everything at a silly scale on purpose. But the drop is the topographic relief you have to work with. So in steep areas versus a very shallow area, there's considerable difference in the relative drop that's available to carry water off our system. What we don't want to have, I'm now running out of drawing space. Let's pick a pretty yellow color. We don't want to have the situation where the pipe is moving uphill. That would require pumping, and that's generally avoided in sewer design. So we can obtain a pretty good preliminary conceptual design using a combination of the rational equation and Manning's equation. This is done without regard to the downstream boundary conditions, and from this preliminary design we would check it using some kind of hydraulic model. SWIM is just one of several that might be used. This class will use SWIM because it's available to us. And let me sketch what I mean by, it's not what I want to have happen. But without regard to boundary conditions, let's suppose we have two junctions like that, and here's our pipe. And our pipe is going to carry nice, yummy water. We'll use cyan. So there's one possible water level, but it's draining out down into this pool, and we don't give much concern to that in the rational method. So in a practical application, it's possible for the downstream boundary condition to change height. This could be a stream or a lake or something, and in practice our hydraulic grade line might look something like that. We have this portion of the sewer that's surcharged. The method that we're about to go through for preliminary design is incapable of accounting for that. So what it's going to do is it'll assume that we can always get water out of the system. It generally provides a pretty good initial design. Often we actually can accept the design without any changes, but we're obligated to check it with a hydraulic model because we need to be cognizant of conditions like are depicted here in the drawing, where the downstream water rises enough to cause a backwater propagation into the sanitary sewer system. And the consequence of that would be where the land surface, something like this black line perhaps, and I drew it badly, but if we get a portion where the hydraulic grade line goes above the land surface, that's generally not acceptable to us in a storm sewer design. We can accommodate that if we have enough vertical real estate by taking advantage of vertical drops along the lines of, we use magenta. So we can have a pipe that goes like that, and then we literally can drop it vertically and continuing working our way downhill. The vertical drops give us the ability to exercise some control over both velocity and a little bit of control over the downstream boundary behavior. So the essence of the preliminary design is we're going to determine the discharge in each pipe. And once we have the discharge in each pipe, we'll use Manning's equation to select the size of the pipe. The version of Manning's equation we'll use is depicted here, where we solve for diameter in terms of discharge, Manning's n, bottom slope, or the slope of the energy grade line if you know it, raised to the 3/8 power, multiplied by 1.33. So that's simply Manning's equation in a circular pipe that's full, rearranged for the unknown diameter. Once we have the value of the diameter and we know the flow rate, it's relatively straightforward to determine the velocity in that pipe, and we'll use that velocity later on to compute a pipe travel time. If you recall this diagram from a few meetings ago, one of the genius things about this design methodology is it's designed assuming that the pipe is full up here. But from our hydraulic element chart, we have two locations where that pipe will carry the same discharge. And so in practice, we expect the pipe to actually operate at about 80% fill depth. And so we have this freeboard up at the top, a little bit of extra capacity to accommodate mistakes. So even though we design it as if it's full, the actual one's going to operate at less than full at the design discharges. So that's kind of cool. A built-in, unintentional factor of safety as a consequence of the design method. And so the next step in preliminary design would be to lay out the system. In laying out the system, we would choose, we need to know what the drainage areas are. So for instance, here's one drainage area. We'll study this in more detail shortly. And here's the inlet, and then that conveys drainage through this pipe to this next inlet, also a junction. There's an inlet here that collects drainage from this area. Someone's done the hard work for us and drawn these areas, and takes flow to that location. These two combine, plus whatever the local flow is, from that area. And there's our there's three drainage areas right there. So we have to identify those drainage areas. We'll need to identify the likely inlet locations if it's new construction. If we're doing a retrofit, we'll generally know where they are. We need to identify the pipes themselves, so they're shown here as these line segments, the outfall, which is shown here, and the elevations, which in this drawing are shown with these contour lines. And I did everything in magenta because that's extra confusing. The drainage areas themselves have a time of concentration associated with them. So this green watershed has an outlet, which we'll call 1.1. So there's the outlet, and we have to determine a time of concentration for flow to that point. That's called the inlet time. And then we would determine the drainage area by measuring it on the map. So we get the area of the green, it's not a rectangle, the green polygon in that picture. And we would determine a runoff coefficient by looking up an appropriate value in a table of runoff coefficients, weighted by what other information we have on the project site, which we don't have in this example. So I know this is in Urbana, Illinois. I know it's a city, but what I don't know is how many trees versus houses there are. So I would need that additional information to come up with a reasonable runoff coefficient. Then, once we have the areas identified, we would start sizing the pipes. And generally what we do is we size the pipes based on the most upstream area. So we get that area, and we would apply hydrology to determine the discharge that that green area will send to location 1.1. Well, that discharge has to flow in this pipe. So we now know the Q that has to go in that pipe, and we would use that to determine the pipe diameter. This Q is fixed. The Manning's end we use is the Manning's end of the pipe. We have some control over the slope because we can lay the pipe in the trench however we choose to design it. So we can adjust the slope. Adjusting the slope might adjust the diameter. Adjusting the diameter and the slope will adjust the velocity. Generally, our design criteria have a velocity requirement and obviously the discharge requirement. And so there'll be a little bit of iteration between the two, until we get a diameter and a slope that gives us good velocity control. And then we would determine the travel time in the pipe. Because we have a time of concentration associated with the inlet, there's a pipe travel time, T sub P. Once we move to this point, we're going to do hydrology again, but we're going to do it on this area, so we need to adjust the time of concentration to account for that pipe travel time. That will make a little more sense, I think, shortly when we get to the example in detail. And then, so from the most upstream outlet, we compute peak discharge as CIA based on the inlet time. We size the pipe from this inlet in order to contain that Q sub P we've just calculated. We add the pipe travel time to the inlet time and then move to the next node. And then we repeat the process. When we get to a junction, in this case junction 2.1, and we're determining what time of concentration to use, we choose the largest of the local inlet time or the upstream node inlet time plus the travel time. And then we'll apply that time of concentration to the entire area that drains to point 2.1. So in the image that's on the screen, that would be the rose-colored area, the yellow, and the green. All those three are going to combine at this point, and we're going to make a rational equation calculation at 0.21 using all those areas. The time of concentration that's used for the intensity is going to be the bigger of the local time to 2.1, which is shown by the green arrow, or the bigger of the green drainage area plus pipe 1.1 to 2.1. If that's a bigger travel time, we use that. Or we use the rose area plus the time in pipe 1.2 to 2.1. And if that's the biggest number, we'll use that. So one of the three will be selected for time of concentration. And then we add up the product of the runoff coefficient and the sub area with each of the other ones and multiply by that intensity, and that becomes the new peak discharge that's going to leave right there. And then we size the next pipe based on that peak discharge. Then we move downstream in the same fashion, always operating from the most upstream tributary to the junction of interest, and accumulate the CA values and the times of concentration as we move downstream. Some checks that we would do at the end would be that the total area adds up for each of the sub areas. So when we get to the end of our design, we should have accounted for all the drainage areas. And if that doesn't add up to the total drainage area, then somewhere along the way we made an error. And it's usually pretty straightforward to go back and find where you made it. And additionally, the time of concentration should be increasing in value as we move downstream. When we get to the outlet, what we'll have is we'll have the sizes of each of these pipes, we'll have the discharges in each of the pipes, and then that would go into a hydraulic model. So for example, we could lay just the pipe model into the SWIM program. We can enter the individual Q inlets directly and check pipe hydraulics. That's one way. That's perfectly legitimate. The second would be to attempt to approximate the rational method in SWIM and just go ahead and hit it with a design hyetograph. That's also perfectly appropriate and probably a really good method. Although there's a bit of hacking required to make that happen. And then we can use the results from SWIM to adjust the design and produce a hydraulic grade line drawing. So the hydraulic grade line would be what the height of the water is in the pipe as we're moving to the outfall. And we would compare that hydraulic grade line to the land surface elevation to ensure that the design flow is completely contained underground in our system. So this next part, we're going to let me see, I'm going to put everything up here. We're trying to make room on the screen. That'll work. Just a teensy weensy bit. We'll go through the storm sewer for Goodwin Street. So this particular example is taken directly from Rational Methods Storm Sewer Design in Larry May's 2008 book entitled Water Resources Engineering, pages 613 to 635. And that is contained in the notes right here. I seem to think we looked at it already, but in case we didn't. So it starts there, and literally I'm following the example that's listed on these pages. And you can tell from the picture there that looks almost the same. The only difference is there isn't any difference. It's literally just directly imaged and placed into the presentation. So that is the source of the example. So we'll return to the presentation. And the method that will be employed is a rational equation design method to make an initial design for subsequent hydraulic analysis. So there's some preparation that has to be done beforehand before we start pencil whipping the problem. We need to determine the area of each contributing area in acres because we're using the rational method. And tools to do that are things like a gauge or a planimeter. That's pretty old school. Or the example we use, Acrobat Pro. Any graphical manipulation tool that has the ability to measure areas. To some extent, the units don't actually matter because we'll do arithmetic to handle that. Is adequate. We also are going to need to determine the rational runoff coefficient for each area, and that's generally a table lookup. Well, that is a table lookup, not generally. So let's go through the areas one at a time. So first we have drainage area 1-1, which is identified as this green polygon at the bottom of the figure. You'll notice that in some cases we actually have some elevation data intermediate. So inlet 1-1, which is the outlet to the green area, inlet into the sewer, is at elevation 732.3 feet. And if you have information like that, we need to record it as well as the actual layout of the drainage area. Now we move to area 1.2, then area 2.1, area 2.2, area 3.1, area 3.2, 3.3, 4.1, 4.2, 5.1, 5.2, 5.3, 6.1, and drainage area 7.1. So those are the individual drainage areas in this example, and somebody has done the work to draw the outlines for us. That's kind of nice. And then we need to measure the actual areas involved with those various polygons. So use an appropriate tool. For instance, in Acrobat Pro, it has the ability to load in a JPEG or a PDF file, and then you can measure areas on the picture, and it usually reports them in things like square inches or millimeters squared. So we need to have a physical scale somewhere. So in this example, the analyst has produced a rectangle that's 400 feet on a side based on the linear scale provided with the drawing. And so when we measure that particular area, that's equivalent to 3.67 acres. Now, Acrobat Pro won't directly report 3.67 acres. It will report something in square inches. It's possible to have it report in units, but you have to manually enter that once, and I find it's easy to just not do it. It's easy to make a mistake, so I find it easier just to write down the conversion factor. And in this particular example, at the scale that it was scanned, the area tool computed an area of 2.43 square inches corresponds to that 3.67 acre region. And so all we do is write down the conversion factor. And in fact, all subsequent measures, even though I'm going to report them as acres in the presentation, they were originally just reported as square inches and then converted to acres using a spreadsheet program as a way to minimize the opportunity to make an arithmetic mistake. So going one drainage area at a time, so drainage area 1.1 has an area of 1.50 square inches, and when we multiply by the conversion factor of 3.67 divided by 2.43, we get a result of 2.26 acres. Drainage area 1.2, we measure it. It turns out to have an area of 1.26 acres. Drainage area 2.1, you can see the outline that's drawn, and it measures out to an area of 3.89 acres. Drainage area 2.2 has a computed area of 0.53 acres. Drainage area 3.1 has a computed area of 0.68 acres. Drainage area 3.2 has a computed area of 0.45 acres. Drainage area 3.3 has a computed area of 1.58 acres. 4.1, 2.01 acres. 4.2, 0.66 acres. 5.1, 1.17 acres. 5.2, 0.66 acres. 5.3, 1.75 acres. 6.1, 0.54 acres, and 7.1, 2.17 acres. So that represents all the drainage areas that this stormwater system is collecting from. And the last portion I'll write down here, to outfall 8.1 is underground, and to the best of my knowledge, when I read the example, there was no additional drainage area. For each area, we then would estimate a runoff coefficient, and it would be usually based on looking up a value in a table. And on the presentation screen is an example of one such table. This particular table comes from the Oregon Hydraulics Manual, Chapter 7, Appendix F, circa 2014. And there's nothing remarkable about this table other than I like that they went to the trouble to promulgate runoff coefficients for flat, rolling, and hilly regimes. And they even tell us what those are. Rolling is ground slope between 2 and 10%. Hilly is ground slope greater than 10%. Flat presumably would be less than 2%. And they've also identified in boldface the areas which would have impervious surfaces. Once we've measured each drainage area, then we would go back and we would assign appropriate values of runoff coefficient. So I don't have the necessary information to do that directly from a table like this, but I do have the example from Dr. May's book, and so I've going to report runoff coefficients that are the same as the example, and they would have originally been determined based on whether this is a gravel pavement or median area cultivated land with some sort of apportionment of impervious and permeable cover to come up with a runoff coefficient. In this case, the one in the example in the book is 0.65. So drainage area 1.1 has an area of 2.26 acres, runoff coefficient of 0.65. Drainage area 1.2, runoff coefficient of 0.80. Drainage area 2.1, 0.70. Drainage area 2.2, 0.80. Drainage area 3.1, 0.70. 3.2, 0.85. Drainage area 3.3, 0.65. Drainage area 4.1, 0.75. Drainage area 4.2, 0.85. Drainage area 5.1, 0.70. Drainage area 5.2, 0.65. 5.3, 0.55. So lots of gardens there. And drainage area 6.1, 0.75. And 7.1, 0.70. And that concludes the drainage areas that this storm drain system collects runoff from. Next, we want to identify and measure the conduit lengths. So again, using Acrobat Pro as an example, but other graphic programs have the same capabilities. We're just going to measure the distances between the node IDs and write those down as the distances of the pipes. In this particular instance, a measurement of 1.51 inches corresponds to 400 feet on the scale map. And so we'll save that scale factor. So every 1.5 inches we measure, we report 400 feet of distance on the land. So pipe 1.1, which connects drainage area 1.1 to the junction at drainage area 2.1, is 415 feet long. And at this point in the example moving forward, I just want to qualify it. The naming convention that's used in the example in Dr. May's book is terrible, because keeping pipes and inlets separate is not easy. And I think it was not malicious. I think it's just a consequence of the way the example was created. So we have pipes named 1.1. We also have junctions named 1.1. Pipe 1.1 connects junction 1.1 to junction 2.1. So it's hard to convey that the naming convention is remarkably important, especially as our systems get quite a bit more complicated than this example. So again, we can make those various measurements for the different pipe IDs. Keep track of the connecting nodes. So this is a connection chart, and we have the inlet IDs, the runoff coefficients, the drainage area, and the drainage ID, and lastly the pipe lengths. And so we're starting to populate a spreadsheet, which is called the Goodwin Storm Sewer example. And so the purpose of the spreadsheet at this point is just to keep track of the different numbers involved. Next, we can get the inlet times for each drainage area. So that can be done ahead of time before we actually apply any hydrologic reasoning. So we now go back to each drainage area and we make an estimate of the longest flow path from the extreme part of the drainage area to the collection point. So in the figure presented in the diagram, the flow path from the remote corner to 0.11 is measured as 0.92 inches. And as it says in the presentation, a best guess effort is sufficient, because it's quite possible that going from this corner to here is actually longer. The difference in this case between those two is going to be pretty small. And there's a lot of other uncertainty involved in the process that getting too fussy about the drainage distances to get the inlet times is unnecessary effort. So using that particular flow path, we would find the slope as 737.5, so that's our best guess of what the elevation in this corner is, down to 732.3, and then we would divide by the length, which is 0.92 inches times 400 feet divided by 1.51 inches, and that comes out to be 5.2 feet in 243.7 feet, or a slope of about 2.1%. So that's actually pretty flat. That's a fairly low slope. A slope, excuse me, I take that back. That's actually not that flat. Slopes of 0.5% are pretty flat. Then we would determine our best guess on what the cover is and apply an appropriate method to estimate travel time, such as NRCS velocity, upland, or Kirby curbage. My personal preference, especially for a problem of this scale, these are pretty small areas, I would probably choose the NRCS upland method. For one thing, it's fairly easy to employ, and it's also quite easy to generate a good collection of documentation of how you obtain the various inlet times. But as always, use the method that makes the most sense for the problem that you're faced with. Kirby curbage is designed for bigger areas than this, and NRCS velocity would be hard to employ in this situation because it's hard to tell where the sheet flow ends. We don't have very long distances, 200, 300 feet, so it would all be sheet flow most of the time. NRCS upland is a method that seems quite appropriate in my opinion. And so here's an example calculation for NRCS upland. And in order to get the inlet time of 11 minutes, which is what is in the original example that this was taken from, I had to use a rather unusual watershed cover type. But we can enter with the slope and the flow path length and the cover type, and it returns a flow velocity, ultimately a travel time in seconds, minutes, hours. We're going to use minutes. And here's the original chart from the NRCS document, and here's a generated graphic, and the red dot shows us where our particular case plots. And so in this instance, we obtain 11-minute travel time for a drainage area that plots in this red dot. And so again, just reiterating, it's unlikely that this part of Urbana, Illinois is forest with heavy ground litter and meadow, but that's the watershed surface type that needs to be used to produce the 11 minutes, which is what is reported in the example in May's book. Then we would repeat this spreadsheet for each drainage area and use that to populate our data collection spreadsheet. And so now we have these inlet times. So these are local travel times for each drainage area to each inlet. And again, it's coincidental that the drainage area ID and the inlet ID have the same designation. That's, in my opinion, not a smart way to do it, but that's the example we're stuck with. And so we would complete that for each of those, and now our spreadsheet's a little bit more populated. Next, we would make our best determination of the junction elevations actually on the land surface, because we'll use those later to determine vertical offsets. We have contour lines indicated here with these dashed lines, we have individual nodes. In some cases, the nodes are very close to a survey point, and we would probably just use that value. In other instances, we're going to have to interpolate between contour lines and survey points to come up with, for example, the elevation at position 3.3. So just like you did for Somewhere USA, it's the same methodology. We employ it here because those node elevations are absolutely vital in our storm drain design and calculations. Well, initially we're going to use those elevations to come up with pipe slopes. And here I just use the surface elevations, and I'll assume that the pipe can slope along the surface. And then later on, when we get further into the design, I'll vertically offset those, maintaining a desired pipe slope to figure out what the actual invert elevations are going to be on the design drawings. So again, we continue to populate our spreadsheet, and now we have drainage area ID, drainage area in acres, runoff coefficient, inlet ID, inlet time, pipe ID, the connectivity list, the length of the pipe measured from the map, and the slope that those pipes would lay on if they were gently laid on the surface of the earth. Our next step is going to be we need to have some way to compute rainfall intensities on these progressively changing drainage areas. And by far the simplest approach is to build an IDF curve for the location, and from that IDF curve we can create a model of rainfall intensity using a hyperbolic power law type structure, and then code that directly into our computational tool. So for this particular example, the basin is in Urbana, Illinois. We can use NOAA Atlas 14 and put the crosshair on downtown Urbana, and from that choose either partial duration or annual maximum series to recover a chart like this, which has intensities as a function of duration for different annual recurrence intervals. And for the example, we'll use a 2-year annual recurrence interval. We download the table, and we'll find that the second column and the time column are useful to us. We probably don't need to extrapolate much beyond 24 hours, so we'll just use the indicated areas that are shown here and put that into another spreadsheet and use the solver routine to fit the equation intensity equals B divided by time of concentration plus D raised to the power E. And we obtain the B, the D, and the E using the solver fit on the spreadsheet. So we'll actually take a look at this spreadsheet shortly. And then once this equation is parameterized, we can use it repeatedly for the necessary intensities for the storm sewer design in this example. So for the example, this is the intensity function that we'll eventually use, and we can actually put that directly into the spreadsheet. And then beginning with the most upstream node, we apply the intensity equation rational method discharge to the inlet. Then we take that inlet discharge, connect it to the next junction, include the pipe travel time, and repeat the process. And that's best illustrated just by looking through the worksheet. So first let's look at the intensity worksheet. Interesting. Okay, classic Excel cannot render the documents. See if we have an old enough version of Excel. So perhaps you all have experienced Microsoft, Apple, and Google consortium making more and more software unusable in hopes it will move to the cloud. I think I might have an old version. Okay, let's try Office. Try Office 2011. Let's see if I can open that. Oh, this thing is really snot. It's not going to render the picture. So this picture is right here, and if it would have actually rendered it, we can adjust the EB and D value. You can see the blue line move around relative to the red markers, which are taken from these two columns. We don't necessarily need the picture to illustrate the method. It's 2011 14.7. See if I can open the version I actually want. Okay, I think that's the one I want. So we'll try one more time. File, open, go to downloads. Yay! So if you have a more recent than 2011 version of Excel, you won't get the picture. Okay. Let's just make some guesses here. Okay, so suppose we start with that. So the values we took from the NOAA Atlas are in this table here, and we've copied them over there. We've taken log time and log intensity for plotting, so we get this on a log-log scale and try to straighten things out a little bit. And here we have the result of our equation. It's of this particular structure right here. So this equation right there is right there, and it's also in this column, and it's taking its parameters B, D, and E from these three cells. And so we can manually try to adjust it. See that 54 didn't help. Maybe we go to 68. And by doing it manually, it's going to take an eternity for us to find a really good fit. So you can see as I'm changing parameter, that's actually not bad. We could conceivably stop there, or we can use the tools that's built into the computer program. So we're going to compute the sum of squared errors, which is determined by taking that inches per hour minus this inches per hour, take the difference between the two, square that, and then we add all those squares up. So each of these is the squared error, and then we sum it up, and then we're going to minimize that number by changing these. And we use the solver to do that. and hopefully it's already set up correctly. Looks like it is. So the objective is cell H15, and the changing cells are up here, and we're going to require that the D term, G3, has to stay bigger than 0, because otherwise it'll tend to drive these D's to a negative number and give us correct from a mathematical sense, but useless from an engineering sense results. So we selected GRG nonlinear because the other two methods are not appropriate, and press the solve button, and it's going to start making calculations. So it's thinking, and you notice each iteration it redraws the graph. And you can instruct it not to stop and let us look at the graph every time, but for learning how to do this, it's worth seeing these steps. And it looks like we're getting close to an answer. At this point, this is probably good enough. Oh, sure enough, it's good enough. So we'll choose OK, and we now have the E, B, and D values that were used in the presentation, and we can copy this formula into the actual management spreadsheet. So let me open that spreadsheet. I don't think this one matters if it gets the wrong version of Excel, so I won't worry about it. So here's our Goodwin Sewer spreadsheet. So I've copied the image just to help me keep track of what's going on. Here's the E, B, and D values that we just computed by analyzing the NOAA Atlas 14 results, wherever they are right here. And now we will go through just a few rows of the spreadsheet in the time we have remaining today. So we're going to start at the most downstream end. So we're going to start at drainage area 1-1. So drainage area 1-1 drains to inlet 1-1. Inlet 1-1 takes flow from that drainage area, puts it in pipe 1-1. So by now you can understand my concern with their naming convention. And pipe 1-1 connects junction 1-1 to 2-1. There's another pipe 1-2, which connects this junction to 2-1, and then there's pipe 2-1 itself, which carries it further downstream. We'll get to that. So let's look at the first pipe number 1-1, which is this pipe right here. Hopefully you can see the cursor moving back and forth. That pipe. That pipe's 415 feet long on a slope of 0.02. It collects flow from drainage area 1.1. That drainage area has an area of 2.26 acres, a runoff coefficient of 0.65. The accumulated area to that point upstream is just the 2.26 acres. The product of runoff coefficient and drainage area is called the CA value. It's 1.469 for this location. And the sum of the CA value from that point to all points upstream is also just 1.469. The inlet time we've already determined is 11 minutes. There is no upstream sewer, so the time of concentration we're going to use is 11 minutes. We put 11 minutes into the EBD intensity equation, which produces an intensity of 4.33 inches per hour, multiplied by the sum CA value, which produces a peak discharge of 6.35 cubic feet per second. So that's the flow that's going to go into pipe 1-1, leaving that drainage area. We apply the diameter equation to compute a required diameter, and that comes out to be 1.11 feet. We would probably select something a little bit more commercially available. So here we're doing 1.25 feet, a 1¼ foot pipe, which would be 15 inches inside diameter. I'm really not sure how available that is, but I know that 1.11 feet is not at all available. Using the used diameter, we can compute a velocity in the pipe, and we can compute a travel time in the pipe. So water spends 1.35 minutes in the pipe at this design flow. We're going to repeat that for pipe number 1-2, which connects extreme drainage area 1.2 to junction 2.1. It's 195 feet long on a slope of 0.4%. The contributing drainage area is 1.26 acres. Runoff coefficient 0.8. Cumulative area 1.26. The CA value 1.008. Some CA 1.008. Inlet time is 9.2 minutes. There's no upstream sewer, so 9.2 minutes is the time and concentration that we'll use. 4.68 inches per hour for a 4.72 cubic feet per second. We compute a diameter. We specify a commercially available diameter, compute a velocity, compute a travel time. And now we get to the interesting pipe, pipe number 2-1. So pipe number 2-1 connects positions 2-1 to 3-1. That pipe's 188 feet long. It's on a slope of 2.45%, and it receives direct flow from drainage area 2-1, and it receives upstream sewer flow from areas 1-1 and 1-2. So let's first analyze the direct connected portion. 3.89 acres, coefficient of 0.7, cumulative area 3.89, CA value 2.72, some CA the same, inlet time of 13.7 minutes, no upstream sewer, 13.7 minutes. There's nothing over here because we haven't decided which time of concentration to use yet. If we include the contribution from pipe 1-1, that has an 11-minute inlet time, upstream sewer time of 1.3 minutes for a total of 12 minutes. If we include 1.2, 9-minute time, 1.21 minute sewer time for a total of 10 minutes. And by convention, we're going to use the largest of those three, which will be the 13.7 minutes, for the time of concentration at location 2.1. Similarly, once we've made that time of concentration decision, we're going to sum up all the CA values from that point upstream, sum up the collective drainage area. So 0.21 receives flow from a total of 7.41 acres. There's the 2.26 acres from area 1-1, the 1.26 acres from area 1.2, and the 3.89 acres from what we called area 2.1, for a total of 7.41 acres. And the CA values, by keeping them in this fashion, if we just add these together, we get the composite runoff coefficient drainage area for that point, which is 5.2. So we use the 13.7 minutes that we selected as the largest of the options, produces an intensity of 3.89 inches per hour, multiplied by the CA value of 5.2, produces 20.24 cubic feet per second, leaving junction 2-1, going into pipe 2-1, making its way to location 3.1. The computed diameter is 1.6 feet. We'd specify a realistic commercially available diameter, compute a velocity, compute a sewer time, and we'll carry those forward into the next group of analysis. So far we've sized this pipe, and this pipe. So 3 pipes have been sized in this first grouping of computations. Going to the second grouping, we're going to size pipe 2-2, which is this pipe Make sure this goes from 22 to 31. We'll size this pipe 22 to 31. So that's a remote pipe, a lateral coming into the main, and then we'll size pipe 31. So let's just first do this pipe 22 to 31. So pipe 22 takes flow from location 22, delivers it to location 31. It's 213 feet long, almost 2% slope. The drainage area directly to the pipe is drainage area 22. It's 0.53 acres, runoff coefficient of 0.8, has a CA value of 0.424, inlet time of 5.2 minutes, no upstream, 5.2 minutes for a intensity of 5.76 inches per hour, multiplied by the CA value of 0.424 for 2.4 cubic feet per second. Compute a diameter, choose a commercially available diameter, compute a velocity, compute a travel time. Next we want to look at pipe number 31, which is this short length of pipe right here. But 31 is has a local contribution of flow, and the flow that comes to it through pipe 2.2 and the flow that comes to it from pipe 2.1. So let's first analyze the local contribution. The local area is 0.68 acres, runoff coefficient of 0.7, the cumulative area is 0.68, the CA value is 0.476, the sum CA is 0.476, the inlet time is 8.7 minutes, there's no upstream sewer, 8.7 minutes is one of the options for a time of concentration, but that location also takes flow from pipe 2.2, which drains a CA value of 0.424 and has an inlet time of 5.2 minutes, a pipe travel time of 0.8 minutes for a total time of almost 6 minutes. And lastly, we consider pipe 2.1, which is this one right, 2.1, this one right here. That pipe has a CA value of 5.2, an inlet time of 13.7 minutes, plus 0.37 minutes of travel time for a total of 14 minutes. So 14 minutes is the time of concentration we'll use to compute the flows that are leaving position 3.1 on their way to position 4.1. And so with the 14 minutes, the total drainage area accounted for is 8.62 acres. The total CA value is 6.1. 14 minutes produces an intensity of 3.84 inches per hour. And 3.84 inches per hour multiplied by the CA of 6.1 gives us 23 cubic feet per second. We compute a diameter. Here I'm choosing a slightly smaller one, but I know 2 feet pipe are commercially available. That's the only one there so far that really exists in real world. Compute a velocity, compute a sewer travel time, and now we're ready to move to the next grouping. And in the interest of getting on to the end, we repeat the process as we move downstream toward the outlet. The trick, if you want to call it a trick, is grouping the sections appropriately. So we move from one node to the next, accounting for everything upstream, and we choose the largest time of concentration where we have multiple entry points coming to a particular node. And so if we apply that repeatedly, we eventually get down to this last group, pipe 7.1. Pipe 7.1 takes flow from location 7.1, delivers it to the outfall, has a total area of 19.61 acres, a CA value of 13.7, a time of concentration of almost 20 minutes, for an intensity of 3.26 inches per hour, produces a total of 44.7 cubic feet per second. That produces would need about a 3.5 foot diameter pipe, and we'll have a velocity of 4 feet per second in the pipe, which is well within the customary 2 to 10 feet per second for sewer systems. We can check this last one fairly easily. So we have roughly 20 acres of drainage area, and so 20 acres with roughly a 20-minute travel time. So 20 times 3 is about 60. So if the runoff coefficient for that 20 acres were 1, we'd get 60 cubic feet per second coming off the whole area. But the runoff coefficient is more like 8/10. So 6 times 8 is 48 cubic feet per second, which is pretty close to the 44 that we computed. So our total area runoff coefficient, regardless of how it's routing internally, is producing about the same expected peak discharge as our small area compositing. So that's reassuring. That means that we probably not unintentionally lost some area somewhere. So to summarize what we've done so far is we've computed the design flows in each of the pipes, and they're listed here in this table, and we would probably correct the appearance of the table and not have 9 digits after the decimal place, because that's just bunk. We have the pipe slopes determined from the land surface elevations right now, pipe diameters in feet and in inches. The next step would be to actually determine the flow velocities and possibly adjust these slopes to get a handle on velocity. But we can look in our table and see if we have any that are absurd. That one's a bit big, so pipe 2-1 might be adjusted, and that one's a bit big. The rest of them are all quite reasonable. And then we would establish the elevations at the top of the pipes. So for example, there's a notation here. It has pipe 1-1, 415 feet long, and the top of the pipe is at 735.8 feet. Let's see if that's ridiculous or not. So 735.8 does not include the required offset. So if that indeed the top of that pipe was at 735.8, it would be sticking up out of the ground. So our next step would be to offset the pipes and start putting them underground, ensuring that we have sufficient cover on top of the pipes so that they don't crush with the traffic. Because you see these pipes are running down the street, so they're going to have traffic loads on them. They have to have sufficient cover, and 3 inches of soil is not enough cover. I'm sure you could engineer a pipe that's more than capable of taking 747 airplanes with 3 inches of cover, but we're not going to want to pay for that. So we would bury the pipes deeper. That's going to have an ultimate effect on the total slope we have to work with, and it's going to be completely controlled by this elevation here, the 715 feet, which is what we want to drain to. And so that constitutes our initial design. From that initial design, we can enter this information, a lot of it we can enter it into SWIM, and then start doing the refinements on the initial design and applying different hydraulic treatments to control both velocity, hydraulic grade line, and elevation. And we'll pick that up in our next class meeting. So that is everything you need to know about the rational method and pipe design. It's actually pretty cool. The first time, if you've never ever done it, the first time it's going to just be utterly confusing. So go through the example, actually read Dr. May's example while you have this in front of you so you can get a good idea of what's going on. Go on, save. And then the second time is still a little confusing, but a lot easier. And by the third time, it'll be pretty straightforward. So we're gonna do this very exercise on the Somewhere USA subdivision. There's another subdivision in Houston that we'll use as an example to reinforce the training that we have to do. And then you'll be ready for attacking Somewhere USA. So that concludes today's lesson. And let me get everything ready for the shutdown. So I want to thank you all for your attention. Are there any questions that arose before I completely disconnect?
The difference between your intensity spreadsheets for the AMS and the PDS?
Can you please state that again? It was a little garbled.
So you have an intensity spreadsheet, and on the back you have a subscript AMS, and then on the other one you have a PDS.
Okay, good question. We'll go look at AMS. AMS is an annual maximum series, and PDS is partial duration series. They usually don't appear much different than each other, but they are fundamentally different ways of explaining intensity. So with the partial duration series, the statistical method picks some particular sentinel value, and every observation above that value is recorded, whereas annual maximum just uses the largest value in any water year. So partial duration series, we can look at the two right here. So the 1/5 should be about the same. That's a 2-year. The main difference comes at the small times and the low recurrence intervals. Let's go here at 100, for instance. So the 1 in 100 partial duration and the 1 in 100 annual maximum are practically the same. So generally.
Can you share your screen, please?
Oh, yeah, that's a good idea. So the partial duration at the 100 year is that column. The annual maximum is that column. These are practically the same. Where they differ is when you go to the shorter annual recurrence intervals. So in the case of an annual maximum, the precipitation frequency is actually almost an inch per hour higher than the equivalent partial duration series. So I tend to use the partial duration series for the 10-year and smaller stuff, and I use whatever one is convenient to obtain for the 10-year and bigger stuff. And that's the main difference between the two. If you Google partial duration series, I think you can get a fairly good description of the theory involved. So they're conveying.
So like the city of Lubbock, when we're doing stuff like this, they say to use like the 100-year storm. So the annual max series would probably be the better one, right?
Yeah, use whatever the design document says, but the 100-year storm, there is a partial duration representation of a 100-year storm and an annual maximum representation of a 100-year storm. Fortunately, at the 100-year and the higher magnitude things, the difference between the two approaches is almost indistinguishable. And I'm looking at these, I mean, they're practically the same number, 10.6 versus 10.6, 7.99 versus 7.96, 6.62 versus 6.59, and so on. So for 100-year, it won't make much of a difference which one you choose. But on the 2-year stuff, it's quite different. And
I see that difference.
and it depends on how recently the guidance manual's been rewritten. If the stuff is from the 80s and early 90s, it's likely that they didn't have access to partial duration series at the time. The theory existed then, but nobody had tabulated it. But if it's something from the late 2000s, they will probably have partial duration series, hopefully specified in the actual design guidelines. But if not, and you have access to both, use partial duration series for the 2-year, 5, and 10, kind of dealer's choice for 25 and 50, and then for 100 and beyond, it doesn't matter. You get the same results. So that's the difference between the two.
I appreciate you taking the time to explain that.
Okay, any other questions? Well, very good. I am going to stop the screen sharing, and I am going to hang up and wish you all a good evening, and I will see you on Thursday, and have a great day tomorrow.